The Resource Description Framework is a family of World Wide Web Consortium specifications originally designed as a metadata data model. It has come to be used as a general method for conceptual description or modeling of information that is implemented in web resources, using a variety of syntax notations and data serialization formats. It is also used in knowledge management applications. The Rdf 1.1 specification was published in 2014. Overview: the Rdf data model is similar to classic conceptual modeling approaches such as integer-euro relationship or class diagrams, as it is based upon the idea of making statements about resources in the form of subject-predicate-object expressions. These expressions are known as triples in Rdf terminology. The subject denotes the resource, and the predicate denotes traits or aspects of the resource and expresses a relationship between the subject and the object. For example, one way to represent the notion the sky has the color blue in Rdf is as the triple, a subject denoting the sky, a predicate denoting has, and an object denoting the color blue. Therefore Rdf swaps object for subject that would be used in the classical notation of an integer-euro-attribute-euro value model with an object-oriented design. Object, attribute and value. Rdf is an abstract model with several serialization formats, and so the particular way in which a resource or triple is encoded varies from format to format. This mechanism for describing resources is a major component in the W3C's semantic web activity, an evolutionary stage of the World Wide Web in which automated software can store, exchange, and use machine-readable information distributed throughout the web, in turn enabling users to deal with the information with greater efficiency and certainty. Rdf's simple data model and ability to model disparate, abstract concepts has also led to its increasing use in knowledge management applications unrelated to semantic web activity. A collection of Rdf statements intrinsically represents a labeled, directed multigraph. As such, an Rdf-based data model is more naturally suited to certain kinds of knowledge representation than the relational model and other ontological models. However, in practice, Rdf data is often persisted in relational database or native representations also called tripler stores, or quad stores if context is also persisted for each Rdf triple. Shapes, or shape expressions, is a language for expressing constraints on Rdf graphs. It includes the cardinality constraints from OSLC resource shapes and Dublin core description set profiles as well as logical connectives for disjunction and polymorphism. As Rdfs and OWL demonstrate, one can build additional ontology languages upon Rdf. History: there were several ancestors to the W3C's Rdf. Technically the closest was MCF, a project initiated between 1995 and 1997 by Ramanathan V. Agarwal at Apple Computer and continued, with contributions from Tim Bray, during his tenure at Netscape Communications Corporation. Ideas from the Dublin core community, and from PICS, the platform for Internet content selection, were also key in shaping the direction of the Rdf project. The W3C published a specification of Rdf's data model and an XML serialization as a recommendation in 1999. The history of prior versions of this work can be found here, indicating a start sometime in 1997. Work then began on a new version that was published as a set of related specifications in 2004. While there are a few implementations based on the 1999 recommendation that have yet to be completely updated, adoption of the improved specifications has been rapid since they were developed in full public view, unlike some earlier technologies of the W3C. Most newcomers to Rdf are unaware that the older specifications even exist. In June 2010, W3C organized a workshop to gather feedback from the web community and discuss possible revisions and improvements to Rdf. Some libraries published their catalog in Rdf, one of them the Hungarian Czar Copyright Car Copyright Me library. Rdf topics, Rdf vocabulary. The vocabulary defined by the Rdf specification is as follows: classes, Rdf, XML, the class of XML literal values, Rdf, property, the class of properties, Rdf, statement, the class of Rdf statements, Rdf, alt, Rdf, bag, Rdf, sec, containers of alternatives, unordered containers, and ordered containers, Rdf, list, the class of Rdf lists, Rdf, nil, an instance of Rdf, list representing the empty list, Rdfs, Rdfs, resource, the class resource, everything, Rdfs, literal, the class of literal values, for example strings and integers, Rdfs, class, the class of classes, Rdfs, data type, the class of Rdf. Data types, Rdfs, container, the class of Rdf containers, Rdfs, container membership prop Rty, the class of container membership properties, Rdf, 1, Rdf, 2. All of which are sub-properties of Rdfs, member, properties, Rdf, type, an instance of Rdf, property used to state that a resource is an instance of a class, Rdf, first, the first item in the subject Rdf list, Rdf, rest, the rest of the subject Rdf list after Rdf, first, Rdf, value, idiomatic property used for structured values, Rdf, subject, the subject of the subject Rdf statement, Rdf, predicate, the predicate of the subject Rdf statement, Rdf, object, the object of the subject Rdf statement, Rdf, statement, Rdf, subject, Rdf, predicate, Rdf, object are used for reification, Rdfs. Rdfs, subclass of, the subject is a subclass of a class, Rdfs, subproperty of, the subject is a subproperty of a property, Rdfs, domain, a domain of the subject property, Rdfs, range, a range of the subject property, Rdfs, label, a human-readable name for the subject, Rdfs, comment, a description of the subject resource, Rdfs, member, a member of the subject resource, Rdfs, see also, further information about the subject resource, Rdfs, is defined by, the definition of the subject resource. This vocabulary is used as a foundation for Rdf schema where it is extended. Serialization formats. Several common serialization formats are in use, including, Turtle, a compact, human-friendly format. N-triples, a very simple, easy-to-parse, line-based format that is not as compact as Turtle. N-quads, a superset of N-triples, for serializing multiple Rdf graphs. JSONLD, a JSON-based serialization. N3 or notation 3, a non-standard serialization that is very similar to Turtle, but has some additional features, such as the ability to define inference rules. Rdf XML, an XML-based syntax that was the first standard format for serializing Rdf. Rdf XML is sometimes misleadingly called simply Rdf because it was introduced among the other W3C specifications defining Rdf and it was historically the first W3C standard Rdf serialization format. However, it is important to distinguish the Rdf XML format from the abstract Rdf model itself. Although the Rdf XML format is still in use, other Rdf serializations are now preferred by many Rdf users, both because they are more human-friendly, and because some Rdf graphs are not representable in Rdf XML due to restrictions on the syntax of XML QNAMES. With a little effort, virtually any arbitrary XML may also be interpreted as Rdf using GRDDL, gleaning resource descriptions from dialects of languages. Rdf triples may be stored in a type of database called a tripler store. Resource identification. The subject of an Rdf statement is either a uniform resource identifier or a blank node, both of which denote resources. Resources indicated by blank nodes are called anonymous resources. They are not directly identifiable from the Rdf statement. The predicate is a URI which also indicates a resource, representing a relationship. The object is a URI, blank node or a Unicode string literal. In semantic web applications, and in relatively popular applications of Rdf like RSS and FOAF, resources tend to be represented by URIs that intentionally denote, and can be used to access, actual data on the World Wide Web. But Rdf, in general, is not limited to the description of Internet-based resources. In fact, the URI that names a resource does not have to be dereferenceable at all. For example, a URI that begins with HTTP, and is used as the subject of an Rdf statement does not necessarily have to represent a resource that is accessible via HTTP, nor does it need to represent a tangible, network-accessible resource. Such a URI could represent absolutely anything. However, there is broad agreement that a bare URI which returns a 300-level coded response when used in an HTTP GET request should be treated as denoting the Internet resource that it succeeds in accessing. Therefore, producers and consumers of Rdf statements must agree on the semantics of resource identifiers. Such agreement is not inherent to Rdf itself, although there are some controlled vocabularies in common use, such as Dublin Core metadata, which is partially mapped to a URI space for use in Rdf. The intent of publishing Rdf-based ontologies on the web is often to establish, or circumscribe, the intended meanings of the resource identifiers used to express data in Rdf. For example, the URI http www.3org 2004 wine mullet is intended by its owners to refer to the class of all mullet red wines by Vintner, a definition which is expressed by the OWL ontology itself an Rdf document in which it occurs. Without careful analysis of the definition, one might erroneously conclude that an instance of the above URI was something physical, instead of a type of wine. Note that this is not a bare resource identifier, but is rather a URI reference, containing the pound character and ending with a fragment identifier. Statement reification and context. The body of knowledge modeled by a collection of statements may be subjected to reification, in which each statement is assigned a URI and treated as a resource about which additional statements can be made, as in Jane says that John is the author of document X. Reification is sometimes important in order to deduce a level of confidence or degree of usefulness for each statement. In a reified Rdf database, each original statement, being a resource, itself, most likely has at least 3 additional statements made about it, one to assert that its subject is some resource, one to assert that its predicate is some resource, and one to assert that its object is some resource or literal. More statements about the original statement may also exist, depending on the application's needs. Borrowing from concepts available in logic, some Rdf model implementations acknowledge that it is sometimes useful to group statements according to different criteria, called situations, contexts, or scopes, as discussed in articles by Rdf specification co-editor Graham Klein. For example, a statement can be associated with a context, named by a URI, in order to assert in as true in relationship. As another example, it is sometimes convenient to group statements by their source, which can be identified by a URI, such as the URI of a particular Rdf XML document. Then, when updates are made to the source, corresponding statements can be changed in the model, as well. Implementation of scopes does not necessarily require fully reified statements. Some implementations allow a single scope identifier to be associated with a statement that has not been assigned a URI itself. Likewise, named graphs in which a set of triples is named by a URI can represent context without the need to reify the triples. Query and inference languages. The predominant query language for Rdf graphs is SPARQL. SPARQL is an SQL-like language, and a recommendation of the W3C as of January 15, 2008. An example of a SPARQL query to show country capitals in Africa, using a fictional ontology. Other non-standard ways to query Rdf graphs include RDQL, precursor to SPARQL, SQL-like, Versa, compact syntax, solely implemented in ForSuite, RQL, one of the first declarative languages for uniformly querying Rdf schemas and resource descriptions, implemented in Rdf Suite. SayRQL, part of Sesame, XUL has a template element in which to declare rules for matching data in Rdf. XUL uses Rdf extensively for data binding. Examples: Example 1, Rdf description of a person named Eric Miller. The following example is taken from the W3C website describing a resource with statements there is a person identified by http www.w3org contact me, whose name is Eric Miller, whose email address is emiller123, example, and whose title is Drive. The resource http www.w3org contact me is the subject. The objects are Eric Miller, mail to e.miller123, example, and Dr. The subject is a URI. The predicates also have URIs. For example, the URI for each predicate, whose name is http www.w3org10pin contact full name, whose email address is http www.w3org10pin contact mailbox, whose title is http www.w3org10pin contact personal title. In addition, the subject has a type, which is person. Therefore, the following subject, predicate, object Rdf triples can be expressed: http www.w3org contact me, http www.w3org10pin contact full name, Eric Miller, http www.w3org contact me, http www.w3org10pin contact mailbox, mail to em@w3.org, http www.w3org contact me, http www.w3org10pin contact personal title, Dr. http www.w3org contact me, http www.w3org02/22 Rdf syntax ns type, http www.w3org10pin contact person, in standard N triples format. This Rdf can be written as. Equivalently, it can be written in standard turtle format as at prefix Eric, http www.w3org contact. At prefix contact, http www.w3org10pin contact. At prefix Rdf, http www.w3org02/22 Rdf syntax ns. Eric, me contact, full name Eric Miller, Eric, me contact, mailbox mail to e.miller123, example, Eric, me contact, personal title Dr. Eric, me Rdf, type contact, person. Or, it can be written in a DF-XML format as. Example 2, the postal abbreviation for New York. Certain concepts in Rdf are taken from logic and linguistics, where subject-predicate and subject-predicate-object structures have meanings similar to, yet distinct from, the uses of those terms in Rdf. This example demonstrates, in the English language statement New York has the postal abbreviation NY, New York would be the subject, has the postal abbreviation the predicate and NY the object. Encoded as an Rdf triple, the subject and predicate would have to be resources named by URIs. The object could be a resource or literal element. For example, in the N triples form of Rdf, the statement might look like. In this example, earn, X states, new %20 York is the URI for a resource that denotes the U.S. state New York, http, Perl org terms alternative is the URI for a predicate, and NY is a literal string. Note that the URIs chosen here are not standard, and don't need to be, as long as their meaning is known to whatever is reading them. Example 3, a Wikipedia article about Tony Benn, in a like manner, given that http, n-wikipedia.org Tony Benn identifies a particular resource, to say that the title of this resource is Tony Benn, and its publisher is Wikipedia would be two assertions that could be expressed as valid Rdf statements. In the N triples form of Rdf, these statements might look like the following. To an English-speaking person, the same information could be represented simply as the title of this resource, which is published by Wikipedia, is Tony Benn. However, Rdf puts the information in a formal way that a machine can understand. The purpose of Rdf is to provide an encoding and interpretation mechanism so that resources can be described in a way that particular software can understand it. In other words, so that software can access and use information that it otherwise couldn't use. Both versions of the statements above are wordy because one requirement for an Rdf resource is that it be unique. The subject resource must be unique in an attempt to pinpoint the exact resource being described. The predicate needs to be unique in order to reduce the chance that the idea of title or publisher will be ambiguous to software working with the description. If the software recognizes HTTP, elements title, it will also know that this title is different from a land title or an honorary title or just the letters title put together. The following example, written in Turtle, shows how such simple claims can be elaborated on, by combining multiple Rdf vocabularies. Here, we note that the primary topic of the Wikipedia page is a person, whose name is Tony Benn. At prefix Rdf, http, www.3 or go to /22 Rdf syntax ns. At prefix vof, http, xml/ns.com 0.1/. At prefix dc, http, elements. http, nwikipedia.org Tony Benn, DC, Publisher Wikipedia. DC, Title Tony Benn. Fof, Primary Topic, a fof, person. Fof, Name Tony Benn. Applications, Sigma, application from DERI in National University of Ireland, Galway, NUIG. Creative Commons, uses Rdf to embed license information in web pages and MP3 files. DOAC, supplements FOAF to allow the sharing of raw copyright SUMA copyright information. Enterprise Architect, MDG technology for ODM. FOAF, designed to describe people, their interests and interconnections. Haystack Client, semantic web browser from MIT CS and AI Lab. Ideas Group, developing a formal 4D ontology for enterprise architecture using Rdf as the encoding. Microsoft shipped a product, Connected Services Framework, which provides Rdf-based profile management capabilities. Music Brains, publishes information about music albums. Nepomuk, an open-source software specification for a social semantic desktop uses Rdf as a storage format for collected metadata. Nepomuk is mostly known because of its integration into the KDESC4 desktop environment. Rdf Site Summary, one of several RSS languages for publishing information about updates made to a web page. It is often used for disseminating news article summaries and sharing weblog content. Resume Rdf, developed to express information contained in a personal resume or curriculum vitae on the semantic web. This includes information about work and academic experience, skills, etc. Simple Knowledge Organization System, a KR representation intended to support vocabulary thesaurus applications, SIOC, designed to describe online communities and to create connections between internet-based discussions from message boards, weblogs and mailing lists. Smart M3 provides an infrastructure for using Rdf and specifically uses the ontology-agnostic nature of Rdf to enable heterogeneous mashing up of information. Many other Rdf schemas are available by searching Schema Web. Some uses of Rdf include research into social networking. It will also help people in business fields understand better their relationships with members of industries that could be of use for product placement. It will also help scientists understand how people are connected to one another. Rdf is being used to have a better understanding of road traffic patterns. This is because the information regarding traffic patterns is on different websites, and Rdf is used to integrate information from different sources on the web. Before, the common methodology was using keyword searching, but this method is problematic because it does not consider synonyms. This is why ontologies are useful in this situation. But one of the issues that comes up when trying to efficiently study traffic is that to fully understand traffic, concepts related to people, streets, and roads must be well understood. Since these are human concepts, they require the addition of fuzzy logic. This is because values that are useful when describing roads, like slipperiness, are not precise concepts and cannot be measured. This would imply that the best solution would incorporate both fuzzy logic and ontology. See also, notations for Rdf, N3, N-triples, trig, trix, turtle, Rdf XML, Rdfa, JSONLD, ontology vocabulary languages, OWL, SCOS, Rdf schema, similar concepts, entity attribute value model, graph theory. An Rdf model is a labeled, directed multigraph. Conceptual graphs. An Rdf graph is a conceptual graph. Website parse template, tagging, topic maps. ISO topic maps are in some ways similar to W3C Rdf. Hypercat, semantic network, other, associative model of data, business intelligence 2.0, data portability, EU Open Data Portal, folksonomy, GRDDL, life science identifiers, meta-content framework, semantic web, SWGL, universal networking language, references. Further reading, W3C's Rdf at W3C, specifications, guides, and resources, Rdf semantics, specification of semantics, and complete systems of inference rules for both Rdf and Rdfs, tutorials and documents, quick intro to Rdf, Rdf in depth, what is Rdf? Rdf and XUL, with examples. GINA, a semantic web framework, external links, news and resources, Dave Beckett's Rdf Resource Guide, resource description framework, according to W3C specifications and Mozilla's documentation, Rdf Data Sources, Rdf Data Sources in Mozilla, the finance ontology semantic web application. Rdf Software Tools, Ultra-Wrapper tool that exposes relational databases as Rdf and SPARQL, Visica a tool that allows to browse a SPARQL endpoint ontology and construct SPARQL queries, Profiles PRNS open source Rdf VIVO ontology-driven social network software developed by Harvard University. Raptor Rdf parser library, listing of Rdf and OWL tools at W3C Wiki, SEM Web Central open source semantic web tools, IntelliDimension semantic web software and tools for Windows, .NET C and SQL Server, listing of Rdf software at xml.com, D2A Server, tool to publish relational databases as an Rdf graph, Virtuoso Universal Server, a SPARQL compliant platform for Rdf data management, SQL Rdf integration, and Rdf-based linked data deployment, Rolex, .NET library and toolkit built to create and browse Rdf documents easily. It abstracts away the level of Rdf triples and elevates the level of the programming work to classes and properties. Alchemy API, web service API/SDK that converts unstructured text into Rdf and linked data. The suite tools listing of 800 plus Rdf and related tools, most open source, and sortable by category and language. A transformation from XML to Rdf via XSLT. RefSuite, the ICS 4th RefSuite, high-level scalable tools for the semantic web, Twinkle, an Rdf to Java bin mapper similar to my but is for relational databases. Rdf Data Sources, Wikipedia, a linking open data community project that exposes an ever-increasing collection of Rdf-based linked data sources,